Hi, welcome to this video series on SMT solvers. Today I'm going to talk about synthesis of a program from a specification using SMT solvers. The plan for today is to show you how to do some more complicated synthesis. Like for example, if you wanted to synthesize, say, a function that will compute the absolute value of an input, okay? However, without using an if statement, okay? So the goal is to come up with an absolute function ourselves, right, through the SMT solver, right? We just specify the rules of the absolute function, okay? So we don't write the code. We just let the computer come up with absolute value function. However, the constraint for the absolute value function is that if the input we send in is, say, for example, greater than or equal to 0, the program should only return x, right? Otherwise, there's something wrong, right? Because it's already greater than or equal to 0. Okay. If we return, if we send in a number, say x less than 0, we want the program to return minus x. Okay, with the caveat that when x is same as the int min, the answer will also be int min, right? Int min is the smallest negative number you could represent using an absolute using a bit vector. So you can't compute minus x of the smallest possible negative number. Okay, that's the fact we know from bit vector representations. Anyway, so here is the absolute function. We want the program to be synthesized automatically given this constraint. Basically, we want the return function to satisfy this constraint. Okay. However, we are going to add some complexity. We don't want any if statement inside the synthesis code. No if statement. No if statement. Okay. The code should be branchless code. So no if then else or loop or whatever. Okay. No if or branch. It's basically branchless code. How do we infer that automatically? So I have been playing with the code synthesizer a little bit, and I wanted to show you what I did so far. Okay. So in my previous sessions, I talked a little bit about code synthesis and shown you some basic Boolean algebra related synthesizer. Today, I'm going to talk about a little bit more complicated example. Okay, so this example is not that straightforward, right? Your absolute function should not use an if statement. Okay, so I didn't search online, and I just thought I will just codify first in the synthesizer syntax, and then I will show you, surprisingly, there is a remarkable matching with the existing approaches, and there are actually some patterns on this topic of absolute value finding, okay? And I will compare that. So let's get straight into the approach that I am going to share with you. And I'm going to share with you this particular file, okay? This particular file is what I put together, right? It's a model I put together to synthesize an absolute value of a number x, right? Okay, and that particular absolute value, okay, so here is the code for that. So what we are writing here is not the complete code for absolute function. We are writing the grammar for the absolute function. So absolute function takes an input x, a bit vector. Basically, a bit vector is just like a regular vector. Instead of numbers, you have zeros and ones. Okay, then the only numbers are zeros and ones essentially. The program takes a bit vector as an input and returns another bit vector. Okay, so the reason I chosen 4 is to just avoid scalability problems, right? However, I'm interested in some kind of a generic pattern that I can generalize it for other number of bit vectors. Okay, in usual programming, we have byte, unsigned char, signed char, int. You hardly have a 4-bit representation, but it's okay for this purpose. For my goal is to be able to explore the state space and come up with a program, right? That's basically what I'm trying to do. So here is the synthesis specification. I wanted to be able to only use bit vector addition, bit vector XOR, and bit vector shift right. These are the 3 operations I allow the generated program to use. And the shift amount, remember, shift right requires how much you wanted to shift right? For example, your specification may look like this, right? You say some x shift right by this is shift left, sorry. Okay, I will just clean this. Your x shift right by say number 5. Okay, in the case of 4-bit, right, the 4-bit is not allowing number 5 anyways, so it cannot be 5. It has to be either 1, 2, 3, or 4, right? But we cannot represent 4 in 4-bit, remember? Oh yeah, one moment. We are talking about a signed number. Okay, so how many places can we shift a bit vector? If you have a bit vector, 4-bit vector, right, we can shift 3 positions. That's the reason these are the possible values we can shift a number x by. Okay, 1, 2, 3, those are the possible values. Okay, just to be clear, to avoid any confusion, we wanted to shift a number. We don't know exactly how much. It could be a right shift by 1 position or 2 position or 3 or 4. 4 is not correct, sorry. So it has to be 1, 2, 3. 4 is undefined behavior. Okay, so these are the 3 possible right shift values. So how are we specifying that? Well, what I did was I actually created a shift amount and mentioned this is 1, right? This is 2, and this is 3. So remember, I'm only working with bit vector of size 4. So this is perfectly fine specification. So my goal now is to specify the constraint, right? How should the absolute function behave like? For a given x, it should return 2 possibilities, right? The x is greater than 0 or greater than or equal to 0 or less than 0. So if the input x is less than 0, this is basically what I'm saying, right? Bit vector sign less than means signed integer. If my bit vector x is LT means less than, right? Less than 0, what am I expecting the program to return? The absolute value of the function better match the negated value of x, right? Otherwise, it's just the regular x. So this is the if then else in the SMT syntax. However, I'm not writing the complete code for an abs function, by the way. I'm only specifying what I am expecting the abs function to do, just to be clear. This is like an oracle, right? This is an oracle the SMT solver will use to synthesize an abs function. The abs function will only use add, XOR, or shift right. Okay, so let's see whether we can infer such a function. Okay, so it looks like we have let's oh yeah, it finished running, and oh, where is my output? And the output is hidden here. Here is the output, right? It is able to synthesize a function like this. Let me explain this, what this is. Okay, this is a nice function it synthesized, and let me explain this. So what it has synthesized is basically this function, and let me explain the syntax. So it may look a little bit cryptic, but it's actually nice, very nice function. What it has synthesized is this algorithm. So we are calling the absolute function. We are passing in the x for which we wanted to compute the absolute value of x, right? So the output is also a bit vector. Okay, so I can just remove this line for readability purpose, right? This is basically what it has returned for us. Let me replace this by 3 because bit vector of 1 and 1 is 3, right? And this is also 3. Okay, so this is much more readable. And for a C programmer or for regular programming language, this is shift right operation, right? So I will replace this by shift right, and this is also shift right. What else is needed? Okay, we are doing a bitwise add, which means I can replace this by x plus, right? Okay, and we are doing an XOR of these 2 things, so I will replace this by this. So essentially, this is what the program it shown. It can remove a lot of brackets. So this is basically what it inferred. I just removed some cryptic syntax for SMT specific syntax. People may not be familiar with it. So this is the output of synthesis, right? And let me just clarify this. Okay, yeah. What is the beauty here is that there is no if statement here, right? If you send in a number negative, it will automatically convert it into positive. And if you send in a positive value, it will remain positive. That's beautiful, okay? There is no if-else statement, as I said earlier. We can actually go back and play with this a little bit, okay? Let's do that. Let's play with this grammar and change it. Let's say we're not allowed to use plus, okay? So how do we do that? So I'm going to go here, right? I'm just going to change this to subtract. Say only use XOR, subtract, and or a bitwise shift right. Okay, let's run this. Okay, it's now running the synthesis where it's trying to come up with an absolute value function. It will only use these operators that we have mentioned, right? Sub, XOR, and or shift right. Okay, it's a little bit slow. I'm running it through my internet. I think it would be different if I have a local installation, but that's fine. We can wait a little bit. In the meantime, I would like to tell one more thing though. See, although I put only 4-bit, you will be surprised to see that if I change to 5-bit or 6-bit, the same pattern holds true. Okay, instead of 4, if I put 5 here, the answer should be changing here to this place. We should change it accordingly. The place where we have these numbers, right? These constants. So 4 becomes 3. If I put 5 here, it becomes 4 here as well, and 4 here as well. So that's really the pattern I was after, right? To be able to infer such kind of programming, such kind of programs. Okay. So let's yeah, here it is. We have gotten the program, which is basically using subtraction this time. You see here's sub. Okay, let me copy this and do the same for you. Okay, for this. Let's try this. Okay, text box. I'll create a text box and I'll just draw this thing. Okay, so now you have another function, right? We can just remove a lot of cryptic syntax, which we don't need. And I will just beautify it a little bit for you. Okay, so it's basically a raw empty syntax. That's why you are seeing some things like that. So this is the inferred program. So let me quickly replace all of these things by something more readable. A shift right is SHR is shift right, right? So that means we are doing shift right by how much? This is 3, and this is also 3, and then we are doing an XOR of these two things, right? XOR of what? XOR of these two things first, and then we are doing a subtraction with this one. So this is basically it. It's amazing. So we inferred another program which has pretty much the same structure as the other program that we just learned. By just replacing sub by add or add by sub, we got another one derived. The interesting fact that I learned is that I didn't see any online publication whatsoever, okay, to be honest with you. I thought this is a pretty cool finding that we could construct such a nice operation for absolute function without using proper if then else, which we will use it in regular programs. But here is a nice way to automate that, because the branches take time. In some computers, if then else is slow. So people avoid taking branch as much as they can, especially in security. We wanted to have linear code as much as we can, constant time code. So we would like to avoid if then else wherever possible. So here is a nice way to infer such small, cryptic, somewhat esoteric code. Okay. What I'm going to do is I will just show you very briefly now something interesting what I found online, and then I can compare it with this one. Okay. So I learned that there is a nice page where people maintain the syntax of this page that I wanted to talk to you about. Absolute value, right? Absolute value. Computing the absolute value without branching. Surprisingly, it had exactly the same structure that I talked about. I didn't see the page, so my variable name was x. It was x plus some mask XOR by mask. And what is mask here? You see here, they have the size of int times char bit minus 1. In my case, I mentioned earlier that if I, let me just go to my page then. You see here, I mentioned earlier, if my bit vector is 4, I have to put 3 here. And exactly they have the same thing here. They reduce the mask, they reduce the amount of shift by 1, right? Because if you take my case, I had my bit vector of size 4. So this whole thing is 4. 4 minus 1 is 3. In their case, if they're talking about a 32-bit number, this will be 4 bytes, 4 into 8, 32 usually, and this is minus 1. So they are basically doing exactly the same as what I did here, and infer exactly this particular pattern automatically, right? I don't know whether anybody came up with this manually or just use some kind of program synthesis approach. I don't really know. That would be interesting to know. And surprisingly, there's a patented version also with a very minor difference, right? The plus becomes minus, and that's basically it, right? They change the plus by XOR, and therefore the XOR gets replaced by minus. And I have inferred the same in my second program. See here, exactly the same. This part, right? The mask is this, and this, I have a XOR and a minus. And then I also have another version where the masks preceded by a plus, therefore the outside is XOR. Okay, it's two different ways to compute absolute value of X without using branches in the code. Okay, is that the only way to do it? Of course not, right? You can keep adding more and more to your grammar and try other different ways. I tried even multiplication, which is not good because multiplication is slow. It does work, but you don't want to have multiplication usually. Okay, that's so to sum up, what we learned is that it is interesting to see that we can infer programs from specifications like this. This is basically syntax guided program synthesis, right? The trick part though is to come up with this kind of syntax, right? And then sort of have a control over how much of the state space you want this synthesizer to explore. That's what I think is the tricky part. I did spend a little bit of time to come up with this grammar, right? You wanted to say what are the operations you would like the synthesizer to explore, and then come up with programs. Okay, just to be clear, I didn't write the complete code, right? I only write the grammar, and then I specify what kind of behavior I'm expecting from the absolute function, right? I'm saying if my input is less than 0, I expect the program to negate the input, right? Otherwise, I expect the program to keep my X as it is. Okay, this is basically the if then else part. This is if then else, and this is the guard, and this is the then part, and this is the else part. Okay, this is part of the SMT solver syntax, and I am using the online CVC4 SMT solver. It also has language synthesis capability, so that's pretty neat. In my previous demo, I shown how to synthesize De Morgan's law. People, if you're interested, please take a look at that. All right, thank you very much. That's all for today.